These are the answers to the AP Chemistry packet on topics 2.1 to 2.4. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. Question 1 says, which of the following correctly ranks the substances listed above in order of increasing ionic character in their bonding? And the three compounds that are listed are barium chloride, BaCl2, cadmium chloride, CdCl2, and sulfur dichloride, SCl2. As you can see on this slide, barium, Ba, and cadmium, Cd, are classified as metals on the periodic table, whereas sulfur, S, and chlorine, Cl, are classified as nonmetals. There is an important difference between a covalent bond and an ionic bond. The usual method used to classify a bond as either ionic or covalent is the following. When we see a metal and a nonmetal, that is generally classified as an ionic bond. And when we see two nonmetals, that is generally classified as a covalent bond. Now, this is a simple criterion that works well for many examples. However, the nature of a chemical bond is more complicated than this. In reality, all polar bonds have some ionic character. There is a continuum between the extremes of covalent bonding and ionic bonding. Now, in an earlier video, I had talked about this PhET simulation on the polarity of a bond. And you can see that I've mentioned that the ionic character of a bond increases with increasing differences between the electronegativities of the bonded elements. If you look on this slide, you can see what happens when the electronegativity of atom B, which is highlighted in green on this slide, how that changes the polarity of the bond. So take a look at as the electronegativity of atom B increases, you can see that that black arrow representing the bond dipole also increases. And the bond character changes from being more covalent to being more ionic as the difference in the electronegativities of the bonded elements increases. Now on this slide, I'd like to highlight some statements from the AP Chemistry course and exam description for topic 2.1, types of chemical bonds. Electronegativity values for the representative elements increase going from left to right across a period and decrease going down a group. These trends can be understood qualitatively through the electronic structure of the atoms, the shell model, and Coulomb's law. The important point about that is that you don't need to memorize the actual electronegativity values of the elements to compare different bonds. All you really need to know are the general trends in electronegativity. The other thing that's highlighted on this slide says that in single bonds, greater differences in electronegativity lead to greater bond dipoles, and all polar bonds have some ionic character. And the difference between ionic and covalent bonding is not distinct, but rather a continuum. Now, in order to answer question 1, we need to rank 3 different compounds in order of increasing ionic character. The ionic character of a bond increases with increasing differences between the electronegativities of the bonded elements. And based on the general trends in electronegativity on the periodic table, we can say that the difference in electronegativity between barium and chlorine is greater than that between cadmium and chlorine. And the difference in electronegativity between cadmium and chlorine is greater than that between sulfur and chlorine. So of these 3 compounds, the compound that has the lowest amount of ionic character would be the sulfur dichloride compound. And the compound that has the highest amount of ionic character would be the barium chloride compound. So the correct answer to question 1 is choice B. And that answer is based on an understanding of the general trends of electronegativity on the periodic table, as well as an understanding of the nature of chemical bonding. Now, let's take a look at question 2. Question 2 says, which of the following has the bonds arranged in order of increasing polarity? What you will probably realize as you take a look at question 2 is that we can use the same strategy that we used to answer question 1. So I'm going to go ahead and put up on the slide the same information that I had highlighted from topic 2.1 that I had talked about during question 1. So electronegativity values for the representative elements generally increase going from left to right across a period and decrease going down a group. And that in single bonds, greater differences in electronegativity lead to greater bond dipoles. So the strategy for answering question 2 is to look at those general trends in electronegativity on the periodic table. And the greater the difference in electronegativity between two atoms, the more polar that bond is. So I'll start with choice A. In choice A, the first bond listed is between aluminum and chlorine. And what you'll see on this slide is that I will highlight the location of various elements on the periodic table as I talk about the various bonds. So there are aluminum and chlorine, which are in the same period. But then when I move in choice A to phosphorus and chlorine, you can notice, based on general trends, that the difference in electronegativity between phosphorus and chlorine would be less than that between aluminum and chlorine. And of course, the third bond listed for choice A is actually chlorine bonded to itself, which would have a difference of electronegativity of 0 because it's the exact same element. So I can eliminate choice A because what happens is, based on general trends, is the difference in electronegativity actually decreases, so those bonds are becoming less polar. And I'm looking for an increase in the polarity. Let's take a look at choice B. Well, we start off with a sulfur-sulfur bond, which would have a difference in electronegativity of 0. And then I would have a bond between aluminum and sulfur. So the aluminum-sulfur bond is, in fact, more polar than the sulfur-sulfur bond. But the third bond listed in choice B is between phosphorus and sulfur. And so I can see, based on general trends, that the difference in electronegativity between phosphorus and sulfur is actually less than that between aluminum and sulfur. So I can eliminate choice B for the following reason. The difference in electronegativity, it decreases after it increases, so it's just not consistently increasing when I compare all three of those bonds. Now, let's take a look at choice C. The first bond listed is between silicon and oxygen. Again, I'm highlighting the location of those elements on this slide. Now I have to move to the next bond, which is between silicon and carbon. So based on general trends, I can see that the difference in electronegativity between silicon and carbon is less than that between silicon and oxygen. And then when I move on to the silicon-fluorine bond, that would be a greater difference. So again, it's not consistent. I can eliminate choice C because the difference in electronegativity between the atoms decreases and then it increases. Let's take a look at choice D and see why that is the correct answer. So all three of these bonds contain the element selenium. So we have selenium bonded to bromine, then we have selenium bonded to chlorine, and then finally selenium bonded to fluorine. So based on general trends in electronegativity, I can say that the difference in electronegativity between selenium and bromine is less than that between selenium and chlorine, and then that would be less than the difference in electronegativity between selenium and fluorine. So it is clear, based on the difference in electronegativity between the two elements, that choice D is the correct answer, because the difference in electronegativity increases as I move from left to right in that set of bonds. Now let's take a look at question 3. Question 3 says the lattice energy of a salt is related to the energy required to separate the ions. For which of the following pairs of ions is the energy that is required to separate the ions largest? Assume that the distance between the ions in each pair is equal to the sum of the ionic radii. So another way to ask this question, looking for the largest lattice energy, is which pair of ions has the strongest Coulombic attractive forces? So we're going to have to consider Coulomb's law to answer question 3. Unlike questions 1 and 2, where we considered general trends in electronegativity, here in question 3, we have to consider what are the important features of Coulomb's law. On this slide, you can see I've highlighted a portion of the essential knowledge statement from the AP Chemistry course and exam description related to topic 2.2. It says, Coulomb's law can be used to understand the strength of interactions between cations and anions. Because the interaction strength is proportional to the charge on each ion, larger charges lead to stronger interactions. Now, on this next slide, you can see information that I had presented when I was talking about Coulomb's law in my video that included topic 2.2. So I'm referring to these two particle diagrams on this slide. And you can see from the particle diagrams that the sizes of the ions are approximately the same in each ionic solid. So the difference between them has to do with the magnitude of the charges on the ions. So in the particle diagram on the right, there's a greater charge magnitude. We can see ions that have charges of +2 or -2 as compared to the diagram on the left where the charges on the ions are either +1 or -1. So a greater charge magnitude would lead to stronger attractive forces between the ions. So the magnitude of the lattice energy of an ionic compound tends to increase as the magnitude of the charges on the ions increases. Now the other factor in Coulomb's law is the distance between the ions. So because the interaction strength increases as the distance between the centers of the ions decreases, smaller ions lead to stronger interactions. So comparing these two particle diagrams, we can see it's not about the magnitude of the charges on the ions, because all of these ions are either +1 or -1. It's about the distance between the ions in the crystal lattice. And so the particle diagram on the left would indicate smaller distance between the ions and a stronger attractive force between the ions. So the magnitude of the lattice energy of an ionic compound tends to increase as the distance between the ions in the crystal lattice decreases. Now let's take a closer look at the 4 examples that we are given for pairs of ions in question 3. So in choices A and B, we can see that the charges on those ions are either +1 or -1. And in choices C and D, we can see that the charges on the ions are either +2 or -2. Let's focus our attention on choices C and D, because a greater charge magnitude would lead to stronger attractive forces between the ions. So we can eliminate choices A and B. Now, taking a look at the difference between choice C and D, one of them contains magnesium and the other contains calcium. So based on general trends in atomic radius, we know that atomic radius tends to increase as you go from top to bottom down a group. So magnesium is smaller in size than calcium. In these two particle diagrams, you can see that because magnesium has a smaller ionic radius than calcium, then there should be a smaller distance between the ions for the pair of ions, magnesium and oxygen, and therefore that would lead to stronger attractive forces between the ions. So based on the principles of Coulomb's law, which includes comparing both the magnitude of the charges on the ions and the distance between the ions, we can say that the pair of ions that has the strongest Coulombic attractive forces and therefore requires the largest energy to separate them would be choice C, the magnesium and the oxygen ions. Now, let's take a look at question 4. Question 4 says, which of the following diagrams correctly shows the potential energy as a function of internuclear distance for the carbon-fluorine bond, CF, and the carbon-chlorine bond, CCl? I'll remind you of some information about topic 2.2. So on this slide, you can see I've highlighted that in a covalent bond, the bond length is influenced by both the size of the atom's core and the bond order, that is, single, double, and triple. Now, in this question, we're not comparing a single bond with a double bond, but we are comparing a carbon-chlorine bond with a carbon-fluorine bond. So the size of the atom is going to affect the properties of that bond. And let me remind you, this is something I had presented in an earlier video when I was talking about topic 2.2. How do you interpret these curves? So here we're looking at a curve for two atoms of hydrogen. Now, when the two atoms of hydrogen are far apart from each other, then there are no significant attractions or repulsions between the atoms, and there is no bond, and the potential energy is close to zero. On the other hand, if you put those two atoms very close together, that is also not a bond or a stable bond, because now you have repulsions between the positive charges of the two nuclei that are too close together. So where is the potential energy the lowest in this diagram? Well, it's right here, and that is the stable bond between these two atoms. Now, looking at this curve, there are two properties of a bond for us to consider. There is the bond length, which would be the location on the x-axis of that minimum in potential energy. Now, when I teach this concept in class, I often refer to that minimum in potential energy as the valley. So I might use that phrase from time to time. So the location of that valley on the x-axis is the bond length. And the depth of that valley, in other words, the difference between zero and the bottom in terms of potential energy, that is the magnitude of the bond energy. So on this diagram, it happens to be 436 kilojoules per mole. That number represents either the energy required to break the bond, or you could also say it's the energy released when the bond is formed. And so a phrase that I often use when I'm teaching this in class, referring to bond energy, is the deeper the valley, the stronger the bond. In other words, a higher bond energy on that curve. So now let's go ahead and focus on the difference between fluorine and chlorine. And so as I had mentioned when I was talking about question 3, and I was comparing the size of magnesium with the size of calcium, we see that the general trend in atomic radius is that the size of the atom increases as you go from top to bottom down a group. So here we can see fluorine and chlorine are in the same group, and chlorine should be larger in size than fluorine. So how does that affect the property of the carbon-chlorine bond relative to the carbon-fluorine bond? Well, if chlorine is larger than fluorine, then the CCl bond should be longer than the CF bond. And so based on that fact, let's see if we can eliminate 2 of the 4 choices that we have here in question 4. So let's take a closer look at diagram C. The location of the curve for carbon-chlorine has a minimum in potential energy that is further to the left relative to the curve for carbon-fluorine. So in choice C, the carbon-chlorine bond appears to be shorter than the carbon-fluorine bond, but we know that's not true, so we can eliminate choice C. And then for the same reason, we can also eliminate choice D. Again, it indicates that that curve for carbon-chlorine has a minimum in potential energy, which is further to the left on the x-axis, indicating a shorter bond. But we know that's not true, So the carbon-chlorine bond should be longer than the carbon-fluorine bond. So now we've narrowed down our choices to either A or B. Let's focus on bond energy. Hopefully it makes sense to you that if a bond is longer in length, then that will make it easier to break. And then vice versa, if you have a shorter bond, then it should be more difficult to break. So here, the carbon-chlorine bond, which is supposed to be longer than the carbon-fluorine bond, should be easier to break, and it should have a smaller bond energy. So take a look at choice B. And as I mentioned earlier, the deeper the valley, the stronger the bond. So the reason why choice B is incorrect is that even though it does get the bond length comparison correct, it's showing that the carbon-chlorine bond with that minimum in potential energy in sort of a deeper valley has a higher bond energy, and that's not correct. So the reason why choice A is the correct diagram in question 4 is focusing on the carbon-chlorine curve. You can see that that is going to indicate a longer bond length because the minimum in potential energy is further to the right on the x-axis, and it has a lower bond energy because the depth of that valley is less than that of the carbon-fluorine bond. So hopefully that makes sense why choice A is the correct answer to question 4. Now let's take a look at question 5. You should notice that question 5 is very similar to question 4. So the difference is that now we're focusing our attention on a carbon-carbon single bond versus a carbon-carbon double bond. So in question 5, it says, which of the following diagrams correctly shows the potential energy as a function of internuclear distance for the carbon-carbon single bond, which is represented as a solid line in these diagrams, and the carbon-carbon double bond, which is represented with a dashed line in these diagrams. I'll remind you what I had mentioned earlier, but last time in question 4, I was focusing on the size of the atom. I was comparing fluorine and chlorine. Now we're focusing on something called bond order. So the bond order is either single, double, or triple. And it says that bonds with a higher order are shorter and have larger bond energies. So what that means is that a double bond should be shorter and have a higher bond energy than a single bond. Knowing that, we can already take a look at these 4 diagrams, and we can eliminate 2 of the 4 choices right away, just focusing on bond length. So the carbon-carbon double bond is shorter than a carbon-carbon single bond. Focus your attention on choice B. You can see that based on that curve for the carbon-carbon single bond, the minimum in potential energy is located further to the left on the x-axis. So that would indicate that the carbon-carbon single bond is shorter. We know that's not true, so we can eliminate choice B. And then for the same reason, we can also eliminate choice D, because if you focus your attention on that carbon-carbon single bond curve, again, you see the minimum in potential energy is located further to the left on the x-axis, indicating a shorter bond, which we know is not true. So now we've narrowed it down to either choice A or C in this question. A carbon-carbon double bond is not only shorter, it is going to be more difficult to break, and it should have a higher bond energy. And as I said earlier, when I was explaining the strategy for question 4, the deeper the valley is on these curves, the stronger the bond is and a higher bond energy. So the diagram that we can eliminate right now would be choice A. So even though it does show that the carbon-carbon double bond is shorter because its minimum in potential energy is located further to the left on the x-axis, you'll notice that that valley for that curve does not go as deep as the other curve for the carbon-carbon single bond. So a lower bond energy is represented by the carbon-carbon double bond curve in choice A, so we can eliminate that. So again, why is choice C the correct answer to question 5? Focusing your attention on that dashed line, we can see that not only is the carbon-carbon double bond shorter in length, it also has a higher bond energy. So hopefully that makes sense why choice C is the correct answer for question 5. Now let's take a look at question 6. Question 6 says the energy required to separate the ions in the sodium chloride crystal lattice into individual gaseous sodium and chloride ions, as represented in the table above, is known as the lattice energy of solid sodium chloride. Which of the following shows the correct prediction for the lattice energy of solid sodium bromide and gives the correct justification? This strategy for answering this question is similar to what I had presented for question 3. We're going to focus on Coulomb's law, and we are looking at the difference between the chloride ion and the bromide ion to answer this question. So focusing on size, Coulomb's law says because the interaction strength increases as the distance between the centers of the ions decreases, smaller ions lead to stronger interactions. So here on this slide, let's compare two different particle diagrams where we're not talking about the magnitude of the charges on the ions, but rather the distance between the ions in the crystal lattice. So I could point to the particle diagram on the left, and I could say higher lattice energy for that compound, smaller distance between the ions, stronger attractive forces between the ions. I could also say the same comparison, but just in another way. If I focus my attention on the particle diagram on the right, I could switch all of those comparative words. I could say lower lattice energy for that compound on the right, greater distance between the ions, and weaker attractive forces between the ions. So the size of chloride and bromide comes from the general periodic trends in atomic radius. So we know that atomic radius increases as you go from top to bottom down a group. So here is the difference between chloride and bromide. We can see that bromide should be larger. So if the bromide ion has a larger ionic radius than the chloride ion, that means we can already eliminate, looking at these four choices, A and C, because in the justification portion, it says that the ionic radius of bromide is smaller than that of chloride, which we know is incorrect. So now, is the correct answer for question 6, is it B or D? Let's take a look at the attractive forces between the ions. So a larger distance between the ions would imply weaker attractive forces between the ions and a smaller lattice energy. So the correct answer to question 6 is not D, but rather B. So the prediction for the lattice energy for sodium bromide would be less than 788 kilojoules per mole. And the justification is that the ionic radius of the bromide ion is larger than that of the chloride ion. And the Coulombic attractions between the ions in sodium bromide are weaker than they are in sodium chloride. Now, let's take a look at question 7. Question 7 says, which of the following diagrams best depicts an alloy of nickel, Ni, and boron, B? So we see 4 different particle diagrams, and the word alloy is mentioned in this question. So I'll remind you of the information from the AP Chemistry course and exam description for topic 2.4, structure of metals and alloys. The 2 types of alloys that you need to be familiar with are interstitial alloys, and they form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. And then the other type of alloy is a substitutional alloy, and they form between atoms of comparable radius, where one atom substitutes for the other in the lattice. On this slide, you can see what I had presented in an earlier video when I was talking about alloys in topic 2.4, and I'm highlighting the particle diagram at the top of this slide for an interstitial alloy, where the smaller black circles are fitting in between the spaces of the larger gray circles. So an interstitial alloy is formed between 2 different atoms in which the atomic radius of one atom is much smaller than that of the other. And one example of an interstitial alloy is steel, which contains iron, Fe, and carbon, C. Now, you might think, just based on this information that I'm presenting at the top right corner of this slide, that somehow you need to memorize these values for atomic radius. And the answer is no, you don't have to memorize the specific atomic radius values, but you should understand the general periodic trend in atomic radius. So in general, atomic radius tends to decrease from left to right across a period, and the atomic radius tends to increase from top to bottom down a group. So you would expect to find larger atoms in the lower left corner of the periodic table, and you would find smaller atoms in the top right corner of the periodic table. So here we can see the relative locations of iron, Fe, and carbon, C, on the periodic table, since carbon is located further toward the top right, and iron is located further toward the bottom left. Hopefully it makes sense that the atomic radius of carbon is in fact much smaller than the atomic radius of iron. Now, the two elements that we're comparing in this particular question are boron and nickel. So just like carbon and iron, we can say a similar comparison that the atomic radius of boron should be much smaller than the atomic radius of nickel based on their relative locations on the periodic table. So what we're looking for in the answer to this question is the particle diagram of an interstitial alloy. And so the only choice that represents the particle diagram for an interstitial alloy is choice A. And you can see in this diagram that the smaller gray circles would be the smaller boron atoms that are fitting in between the spaces of the larger white circles representing the larger nickel atoms. And just as a point of comparison, choice C in question 7 would represent a substitutional alloy. Again, the correct answer for question 7 is choice A. Now, let's take a look at question 8. Question 8 says, which of the following diagrams best illustrates how a displacement in an ionic crystal results in cleavage and brittleness? The information that you need to answer question 8 comes from topic 2.3 in the AP Chemistry course and exam description, the structure of ionic solids. Here is a very brief essential knowledge statement from topic 2.3. It says, the cations and anions in an ionic crystal are arranged in a systematic, periodic, three-dimensional array that maximizes the attractive forces among cations and anions while minimizing the repulsive forces. So in an earlier video, when I was presenting information on topic 2.3, I had presented the information on this slide. It says, ionic solids tend to be brittle, and they can be cleaved along well-defined planes. The following diagrams can be used to explain the brittleness of ionic solids, and here is a short video clip that explains what's going on here.
In this atomic scale view of sodium chloride, when the crystal is struck, ions with the same charge are moved near each other. Since like charges repel, the crystal cleaves into two pieces along the plane where it was struck.
So the reason why an ionic solid is a brittle solid is because when you apply a stress to the ionic crystal, the planes of the ions slide in response to the stress, and then repulsion between ions of like charges lead to separation of layers, and the ionic solid can be cleaved along well-defined planes. So in question 8, the diagram that best shows what happens to an ionic solid before displacement and after displacement would be choice A. Now, let's take a look at question 9. Question 9 says white gold is a common alloy of gold, Au, and palladium, Pd, that is often used in jewelry. The atomic radii of the metals are given in the table above. A particular ring is made from an alloy that is 25 mole percent palladium and 75 mole percent gold. Which of the following represents the correct particulate diagram of the solid alloy? So I'll remind you what I had presented earlier about alloys. There are two different types of alloys. There's interstitial, which I had talked about earlier, and the example was iron and carbon to make steel. But there's also substitutional alloy. A substitutional alloy is formed between two different atoms whose atomic radius values are similar to each other. So one example of a substitutional alloy is brass, which contains a mixture of copper, Cu, and zinc, Zn. So copper and zinc have atomic radius values that are identical, and here in this question, the atomic radius of palladium is 140, and the atomic radius of gold is 135. Those numbers are very similar to each other. So we are looking for a substitutional alloy in terms of our particle diagrams. Let's go ahead and eliminate any particulate diagrams that show an interstitial alloy, because that's not what we have here. So let's go ahead and get rid of choices C and D, which, as you can see, there's smaller circles that are fitting in between the spaces of larger circles. So we do not have an interstitial alloy. We're looking for a substitutional alloy, so we can narrow down the choices to either A or B. Now, it did say that a particular ring is made from an alloy that is 25 mole percent palladium and 75 mole percent gold. Since gold is present in a larger amount and it's represented as white circles in this diagram, then the correct answer to question 9 should have more white circles than gray circles. And then again, 25 and 75, that would be a roughly 3-to-1 ratio between the gold and the palladium. So based on that information, the correct answer to question 9 is choice B, which shows a larger number of atoms of gold compared to atoms of palladium in that particle diagram. So question 9 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.